Triacylglycerols, two things that really can be said about them is their function and then their structure. Functionally, they really just have two jobs, really one job more so than the other, but it's at the cellular level it has one job, and at the physiological level this has many jobs. So this is the storage form for food. So say that we eat some sugar or some protein and meat or some fat. Ultimately we're going to have to break that down, but the format that we're going to use to store it is these triacylglycerols. And the reason why this is good is because, one, it's stable. It can last a very long time. It's not going to rapidly decompose or be readily broken down. We have to put a lot of energy into breaking them. But in their anhydrous form, which is the form that most nonpolar molecules are, this thing has 6 times more energy per gram than a carbohydrate. So this is why we use this as a storage molecule. Because we, as animals, and really as mammals as well, specifically though, have a huge metabolic need. I mean, I have to eat 3 times a day usually. Sometimes I decide to eat more than that, but usually just 3 for the purposes of survival. The rest, it's just because you're fucking bored. But this has so that's the function at the cellular level. Other functions that we could say that it does serve would be as shock absorption, right? When I worked in EMS, I actually saw this one guy who was so fat that he got shot in the gut with a .22 caliber pistol, and it didn't harm any of his vital organs because he was so fat that, like, I mean, sure, he's going to die of a massive coronary later on, but still, I mean, he didn't die that day because he was fat. Anyway, so shock absorption is a great one. Another one would be temperature insulation, physiologically speaking, at the level of organisms and tissues. I always have to get in fights with my roommates that I used to live with, because one of them was kind of a bigger guy, and he was like, always had it on like 60 degrees or something. He was like, you're a little bitch. And I would always respond with that, well, you know what, my friend? You have a surface area volume ratio that is highly maximized. And that was my scientific way of calling him fat. So that's the function of triacylglycerols. Let's get into the structure of it, because the structure of it is, I mean, they're all kind of similarly related. They're all fats, right? So they're all going to have similar structures involved in them. But for the purposes of this, I'll switch colors. The structure is a glycerol alcohol backbone, and attached to that glycerol backbone we have 3 fatty acid chains. Glycerol consists of 3 carbons attached to it, and each and every one of those would be a alcohol group. I'll draw the synthesis later, but I'm just kind of showing a generalized overview. There's the O. These were once OHs, but since they're used to catalyze a bond formation, we tend to have them released in the binding of the fatty acids. I'm just going to represent this in the abstract as an N, meaning it can go on longer if it needs to. It can be double bonded, single bonded, whatever. Have certain degrees of unsaturation to it. So this is what you would have as a structure of it. Here's your glycerol backbone. This is the 3 fatty acid chains. This is the ester linkage linking this together, the C, the double O, and the other C there. And some notes that we want to make is that this is formed by, I'll do it in white, dehydration synthesis. Dehydration synthesis. This is a really common thing in biology, is that biomolecules are synthesized from really stable compounds, and so they have very strong reactive species in them. So let's just go ahead and imagine, I'm just going to draw one of the carbon atoms reacting in my glycerol backbone. But you can imagine I have the glycerol here. Each and every one of these is an OH. And he comes into the vicinity of a free fatty acid, which, if you remember what a free fatty acid is, it's basically just a hydrocarbon chain with a what? Carboxylic acid group attached to it. I'm just going to abbreviate that as R just to simulate that, or I could maybe just draw it as a carbon there. I'm going to stick with R. Anyways, the long carbon chain here, that's not important. But what's ultimately going to happen, and the mechanism isn't superbly important because this is not a majors class, is that these guys over here are going to be released and they're going to be removed. So we're having H2O is being taken out of our system, and that's going to form these bonds. I imagine the specific mechanisms of it, if you're really that curious. The OH group, the hydroxyl group here, acts as a nucleophile, which attacks here, which moves this up here, which acts as the OH group as a leaving group. It leaves, and that's what you get. And then we have deprotonation of our oxonium ion. That's, again, not important here. What's interesting to me is that I can't state off the top of my head whether or not these reactions are formed through the use of a complicated enzyme cascade, or whether they're formed through a straight enzyme, I would assume that we need to have them form enzymatically because of the nature of this reaction here. But again, it's formed by dehydration synthesis. And anytime we have a fatty acid chain linked to a glycerol, we're using dehydration synthesis to give us an ester linkage.